So we proved the quotient remainder theorem, which is kind of the workhorse. That's the most important theorem of all of this. And we used that then to prove some basic facts about divisibility and just the properties of modulo. But now I want to turn to some more of the properties of modulo, and I'm going to try to zero in on arithmetic expressions. Okay, so here's what I know. I have a number a, and modulo n is equal to a prime. Okay, and I have a number b, which modulo n is equal to b prime. Okay, so now my question is, what exactly is a plus b mod n, right? And what I would like the answer to be is a prime plus b prime, right? I mean, that seems to make sense. Actually, it's not really, okay? So we can try, like 10 mod 7 is 3, 16 mod 7 is 2, okay? 26 mod 7 is 5, so that encourages us to think that, in fact, I can just add a prime plus b prime, or a mod n plus b mod n. But the reason that doesn't work is because there's no guarantee that it's actually less than or equal to n. So 10 mod 7 is 3, 12 mod 7 is 5, but 22 mod 7 should be equal to 1, 3 times 7 plus 1, not 8, right? 8 is actually too large, okay? This is too big, and because it's greater than 7. Okay, in fact, greater or equal to 7 would be problematic. All right, but it does give us an idea, right? Maybe that's a good start. Add those two, and then make sure it's not too big. And the way that we can make sure it's not too big is by taking the modulo operation. Okay, so a plus b mod n is just a mod n plus b mod n modulo n, right? That's the only thing that makes us into trouble. Okay, so how can we do this? Well, a is equal to k1n plus r1, quotient remainder theorem. B is equal to k2n plus r2, and of course, R1 and R2 are in the appropriate range. Okay. All right. So a plus b is k1 plus k2n plus r1 plus r2, and what do we have? Well, 0 is less than or equal to r1 plus r2, right? I mean, this is what we have. I want to claim that that's the remainder, but it can't quite be. Okay, because it could be greater than or equal to n. Okay, so now let's think about it. R1 plus R2 is K3n plus R1 plus R2 mod n. This is the quotient remainder theorem again, right? Is some number is equal to K times n plus the remainder of that number base n. So what I can now write is AB is K1 plus K2 plus K3 times n plus R1 plus R2 mod n. Okay. So what's the remainder of this whole thing? The remainder of this whole thing is precisely that. Okay, this must be the remainder, and the remainder because of quotient remainder theorem, uniqueness part. Okay, so yeah, if you add two numbers modulo n, right? Then what you get is actually just the sum of the remainders, but you have to be careful to do that modulo n so that they're not too big. Okay. Let's see what else we can prove, right? What about a times b? Okay, so one more time, what we want is for that to be a mod n times b mod n, right? I mean, that's what we would like, and it almost works, right? So we have 10 mod 7 is 3, 16 mod 7 is 2, 160 mod 7 is 6. That's just perfect, right? So a b mod n is a mod n times b mod n, but you know better, right? It's too big. So here's the counterexample. 10 mod 7 is 3, 12 mod 7 is 5, 120 mod 7 should be 1, it should not be 15, right? That number's way too big. So let's see. We'll just take that product and then do mod n. Does that actually work? Okay, so as before, we can write a and b in terms of n and some remainder r1 and r2. Okay, so a times b, we just multiply it out. Okay. And when we multiply it out, we get this is k1, k2 times n plus k1 times r2 plus k2 times r1, all of that times n. I mean, this is just straightforward multiply it out and factor, right? Factor term. And then I'm left with a one term that doesn't have an n in it, which is r1, r2. Okay, so that's the candidate for remainder, right? But it could be too big, so we'll just try to rewrite things a little bit, because R1, R2 is some K3 times n plus the remainder of that mod n. That's just the quotient remainder theorem. And so the whole expression now becomes this. This part is what we had before, okay? This comes from AB equals plus R1, R2, okay? And then the K3, that's from breaking up R1, R2, okay? So what we're left with must be the remainder of AB mod n, okay? Okay, it's unique, again, quotient remainder theorem, right? So notice that both the proofs for A plus B and A times B were essentially the same, right? The same argument. We just say, oh, write A and B using the quotient remainder theorem. Actually do whatever operation, add the results, multiply the results, and then take a look at the term that doesn't have an n on it. That's the remainder. Oh wait, it could be too big, so go ahead and divide it and get its remainder. Lump the part that has n with the other parts, and now quotient remainder theorem, that must be unique. That must be the remainder. So how about differences? Well, how do I find A minus B mod n? Well, A minus B is just A plus minus B, right? So it's A plus minus 1 times B. So we can actually just do this. A minus B mod n is A mod n plus minus 1 mod n times B mod n, and then mod n the whole thing, right? So we have an expression for it. It's a little ugly, okay? But we can actually make that simpler because minus 1 times B mod n is minus 1 mod n times B mod n, right? So this whole thing here, right? That whole thing is just, it's just minus 1 times B mod n, right? So what we have is A plus minus 1 times B, okay? So there's a simpler expression, which I think is the expression that you would expect. A mod n minus B mod n, and then take mod n just in case, okay? A over B. Well, let's see what we could do. We know A over B is A times 1 over B, right? So we, no, okay? This is as far as we get. And here's the reason. Let's say that I want 4 divided by 5 mod n. 4 divided by 5 isn't even an integer, so I can't take his remainder mod 7. What do we do? Actually, there is something that we can do. We can just say, let's not talk about it. It just doesn't work, okay? I can also tell you, you know what? You're going to see this in another class. Worry about it then, okay? And that's good enough, okay? But I just want to give you a hint, okay? And the hint is this. 5 times 3, okay, mod 7 is equal to 1, okay? So all this is saying is that 5 times 3, and I'm treating that as mod 7 equals 1, right? So interesting, right? So basically, I can say that 5 inverse is equal to 3, you know, and I need to say mod 7, okay? So if I want to divide by 5, what I'm going to do is multiply by 5 inverse, and that's actually 3, okay? So 4 divided by 5 is really 4 times 5 inverse, okay, right? And that's actually 4 times 3, right? And this is all mod 7, right? And that's actually equal to 5. Okay, so 4 divided by 5 is actually 5 mod 7. Okay, the only reason that I kind of show you that, right? And like I said, this for another class. But if you think about cryptography, this operation is actually super important in cryptography. And just in case you didn't know, cryptography is well, large parts of it. Certainly all of the RSA encryption stuff, the stuff you see when you do HTTPS. All of that is based on modular arithmetic. So, and this kind of inverse function is really critical there. I just showed you what it means to do divisions based on multiplicative inverses, okay? But I just want to show you that that actually works really nicely when it should, okay? So 2 inverse mod 7 is 4. That's because 2 times 4 is 8, which is equal to 1 mod 7. 6 divided by 2, 6 times 4 mod 7, that should be 3, right? And yeah, you know, it's 24 mod 7, 21 plus 3, so 3 is the remainder. And so what we have is that 6 divided by 2, that's actually an integer, okay? In general, right, when I divide two things, that isn't the case, right? I end up with an integer. But when I do, then this method of finding a multiplicative inverse actually works just fine. So at least it's a decent definition, okay? All right. How about exponentiation, right? And this is an important operation, like I said, for example, for encryption. Okay, so a to the b mod n is actually not the same as a mod n to the b mod n. Okay, that's too much to hope for. So the exponent actually counts the number of multiplications that are happening, and you can't just say, oh, well, I'm multiplying something by itself 3 times. That's the same as multiplying something by itself 10 times. No, it isn't, right? So this really doesn't work. Okay, so we need to do something different. Okay, because it's really important. Okay, then what it comes down to is I'm going to have to do the multiplications mod n. I mean, there's just no other choice. Okay, but it's an important operation, so I want that to be fast. And we have a couple of tricks. So here's the first one. I could figure out what a to the b is, and then take the modulo, right? Then actually divide by n and then do the thing, right? But if I look at a times a times a times a, okay? And I'm doing this mod n, okay? Well, actually, because of the way multiplication works, I could have just done a times a mod n, right? And then multiplied it by a mod n, and just do this n times, or k times, or I guess b times, right? Yeah, these two are identical because of what we've already seen about multiplication, right? I mean, we actually showed that because of multiplication. So the advice, right, is don't wait till the end to take the modulos, because the trick to being efficient is to work with small things, right? It's fast to do small things. It's slow to do big things. So every time that I multiply the numbers, the number of bits actually doubles. So if I multiply two 8-bit numbers, I need 16 bits to hold it. So don't do that, right? Don't keep making larger and larger numbers. Just focus on what we have, right? So, do the mod n at every step. That is huge. That makes a gigantic difference. Okay. Now, then the other kind of speed up that we can do is we don't have to multiply a by itself b times, okay? Because, for example, if I have a to the 2k, right, I want to figure out what a to the 8th is, right? What I'll do is I'll figure out what a to the 4th is and then square that. Okay, so, oh, by the way, a to the 4th is just a to the 2 squared. So what I have is a to the 2 squared, right? How many multiplications do I need? I need 3, right? A times a, and then whatever that number is times itself, and then whatever that number is times itself. Boom, done. That's 3 multiplications as opposed to 8. Much better, right? In general, it'll actually lower the number of multiplications by a log factor, right? So it's very much significant. So that's actually what all these encryption routines will do. Okay, these are the 2 bits that are used to speed up encryption.